Hello and welcome back. We are in Chapter 8 of Materials Kinetics on diffusion and crystals. Last time in Chapter 7, we covered the microscopic basis for diffusion in terms of atomic hopping, and then connected that back to macroscopic diffusivity in terms of Fick's laws. Today, we are going to consider the atomic mechanisms for diffusion in crystals. Specifically, we're going to be considering single crystals, initially a perfect crystal, and then a single crystal with point defects. Then we're going to consider a couple of specific atomic models for diffusivity in single crystal metals. First, interstitial diffusion in a BCC metal, and then diffusion via the vacancy mechanism in an FCC crystal. Then we're going to discuss diffusion with correlated jumps and then get into diffusion in ionic crystals. This is going to include both our description of ionic crystal defects in terms of Kroger-Vink notation, as well as an example of diffusion in sodium chloride, where we can show how different mechanisms can contribute to intrinsic and extrinsic regimes of diffusion. So recall from last time that we had our macroscopic definition of diffusion, and this description was based on continuum equations for the fluxes of particles and the evolution of their concentrations. In other words, Fick's first and second laws of diffusion. This involved defining a diffusivity D, also known as the diffusion coefficient, which is the kinetic factor related to diffusive motion in a macroscopic sense. Then we also introduced the microscopic description of diffusion in terms of individual particle displacements. And this can be modeled as a series of thermally activated discrete movements called jumps. The rates of those jumps depend on both vibrational frequency as well as the excitation energy relative to the thermal energy of the system. So last time that was in a general sense. Today, in this chapter, we're going to consider atomic jumping in real crystals. Now, the atomic mechanisms for diffusion in real crystals depend on many factors. They depend on the crystal structure, the nature of bonding in the crystal, the nature of the diffusing species, and so on. And within a single crystal, four of the key mechanisms are the ring mechanism, the vacancy mechanism, the interstitial mechanism, and the interstitialcy mechanism. And I will show you each of these four mechanisms in the upcoming slides. So first is the ring mechanism, and this is the mechanism of diffusion in a perfect single crystal. So if there are no defects, the way for an atom to diffuse is by rotating its position with at least 3 atoms involved in this cooperative motion. This is kind of like if you are stuck in a crowded elevator and there's no free space for you to get into. The only way to move from one position to another is to undergo this type of rotational motion involving at least 3 people. It needs to involve at least 3 because if there are only 2 atoms here, the atoms cannot pass through each other due to Pauli's exclusion principle. So at least 3 atoms must be involved with this ring mechanism, if not more. And if we consider the motion of this atom here that is highlighted in red, this can bump into the atom to its upper right, which can then displace another atom, which then goes into the original position of the red atom. And this ring type of cooperative motion can repeat itself over and over again in order to lead to some net movement of the red atom. Now, the advantage of this mechanism is that it can occur even in the absence of any type of defect in the crystal. The disadvantage is that it requires a cooperativity of the motion, so the cost of energy is more compared to if defects were actually present. Now, one of the defects that really helps to facilitate the motion of atoms is vacancies. So consider this case where now we have a vacancy on this lattice point in the crystal. And now this red atom doesn't require any other atoms to move in order to move into this neighboring position. So with the vacancy mechanism here, the energy barrier for the atom to make that motion is significantly less compared to the ring mechanism. And so that's the main advantage, is that the presence of that defect, the vacancy defect, really lowers the activation barrier and eliminates the need for cooperative movement. The disadvantage of this vacancy mechanism is that once the red atom hops into the next location, the most probable thing for it to do is actually to hop back into its initial location, and then the net motion in that case would be 0. So if we want to have net migration here, we need to have other atoms moving into the vacancies. As other atoms move, the vacancy is moving to wherever those atoms had left behind, and then that can enable the forward motion of the red atom. Another mechanism in a single crystal is the interstitial mechanism. With the interstitial mechanism, we are considering the diffusion of a small interstitial species that occupies these interstitial sites on the lattice. For example, if you've got a small atom here that's occupying the interstitial site in this lattice, and if the concentration of that dopant is small, then the other nearby interstitial sites are most likely vacant, and they can hop between interstitial sites. And the activation barrier there involves just pushing these two atoms apart a little bit so that the smaller atom has enough room to squeeze through. And then the diffusion occurs by hopping between these interstitial sites. So the advantage is that it's still a relatively low energy cost. The disadvantage is that this mechanism only applies for these small dopant atoms that can actually occupy interstitial sites. Now, if you take the word interstitial and add the letters CY to the end, you get the interstitialcy mechanism. With the interstitialcy mechanism, this occurs when atoms from the lattice can occupy interstitial sites, at least temporarily. For example, if you had this substitutional atom here occupying this interstitial site, the interstitial site is energetically unfavorable for this atom, and so it wants to fall back into its lattice position. But to get back to its lattice position, it needs to push another atom out of the way. So this atom, when it falls into its lattice position, pushes another one into an interstitial position. This one is then going to push the red atom off of its lattice site and into an interstitial. That red atom is then going to push another atom, and this process continues. So at each step here, one new atom gets pushed into an interstitial site, and then it subsequently pushes another one off of its lattice site into an interstitial. The advantage of this mechanism is that the diffusion occurs based on the actual atoms from the lattice or substitutional atoms. The disadvantage is that the energy cost here is more compared to just the interstitial mechanism or the vacancy mechanism. So to summarize, interstitial diffusion is the dominant mechanism for diffusion of relatively small impurities in a host crystal. An example of that would be diffusion of hydrogen in a crystal. The vacancy mechanism is the primary mechanism of self-diffusion in most metals. The interstitialcy mechanism can also contribute significantly to self-diffusion in metals. But in most real materials, the diffusion is going to occur by a variety of different mechanisms. The mechanisms that we've covered here are just within a single crystal. In some of the subsequent chapters, we will deal with other methods where dislocations, grain boundaries, and so on can lead to even faster diffusion. So recall from last time, we had the Einstein diffusion relation, which is one of the equations that connects the microscopic and macroscopic descriptions of diffusion. This describes the mean squared displacement of atoms in the microscopic view and relates it to our macroscopic diffusivity by taking the second order moment of that concentration function. So in 3 dimensions, the mean squared displacement of the atoms is equal to 6 times the macroscopic diffusion coefficient d times time, t. So if we apply this Einstein diffusion equation to some simple hopping events that occur in a body-centered cubic iron sample, for example, what if you have dopant carbon atoms that are occupying interstitial sites in BCC iron? How can we describe the hopping of those interstitial carbon sites in this BCC unit cell? So first we need to construct the BCC unit cell of iron. That involves putting the atoms on each corner of the unit cell as well as one in the middle to make it body-centered cubic. From there, we can consider that there are three possible interstitial sites for the carbon to occupy. It can occupy this interstitial site on the left face here, shown as number 1. It can occupy the interstitial site on this edge, shown as 2, or on the upper face here, shown as 3. And these, of course, get repeated on all of the edges and faces once you repeat the unit cell in all directions. What we're going to consider specifically is hopping of the carbon atom from this alpha plane here, this blue plane that cuts through the middle of the unit cell, labeled as alpha, hopping from that plane to this beta plane here, this gray plane, which is in the front of the unit cell. So this would be hopping along the y direction as labeled here. Now, the interstitial diffusivity, d sub I, would be equal to the jump rate. So this is the rate of jumping, 1 over time dimensions, times the hopping distance squared, divided by 6, then for three-dimensional diffusion from the Einstein equation. And let's consider now the contributions to the hopping from both the 1, 2, and 3 sites. First, we're going to assume that if you have some concentration of carbon atoms, if that concentration is C prime, let's assume that the concentration is divided equally among these 3 sites. So 1/3 of that would be at site 1, 1/3 of it at site 2, and 1/3 of it at site 3. Now we need to consider what is the contribution of the flux from the alpha plane to the beta plane for each of these cases. For this interstitial site 1 to jump from the alpha plane to the beta plane, it can just go ahead and make that jump. There's nothing stopping it. So we've got the concentration of the species there at 1, which is 1/3 of our total concentration of carbon impurities, times the jumping rate here, gamma. Likewise, for site 3, it's the same thing. It can hop from the alpha plane to the beta plane, and there's nothing there to stop it. So again, that is a C prime over 3 times gamma. Now, site 2 is different because there is an atom here at that exact position on the beta plane, which means that any carbon atom that is sitting here on this upper left edge interstitial site is unable to contribute to the flux along this y direction. So this contribution here is 0 because there's an atom there that is blocking the pathway for it to hop. Therefore, the total flux is just summing up the contributions from 1, 2, and 3, and so it's 2/3 of C prime times gamma, since site number 2 doesn't contribute at all. Let's consider one more case here of diffusion in a single crystal metal. Let's consider diffusion now via the vacancy mechanism in a face-centered cubic crystal. So here's our face-centered cubic unit cell, where you've got one atom here on each of the corners and one atom on each of the faces. And because we're dealing with the vacancy mechanism, let's take away one of those atoms here on this face, and we'll have that as the vacancy. Now, from the geometry of the FCC unit cell, we know that each position here has 12 nearest neighbors. And so the overall jump frequency of the vacancy would be equal to 12 times the individual jump frequency of one atom into the vacancy. Each one of these vacancies has 12 nearest neighbors. And so if you take each one of those individual jump rates multiplied by 12, that would give you the total jump rate of the vacancy itself. Now, the vacancy diffusivity, d sub v, is therefore the jump rate, gamma sub v, times the jump distance squared, r squared over 6. So using this equation here, this is 12 times the individual atomic jump rate divided by 6. And then the distance here, the distance between nearest neighbors on the FCC unit cell, is our unit cell parameter here, a, divided by the square root of 2. So this r squared becomes a over the square root of 2 squared. Now what happens is the 12 divided by 6 divided by the square root of 2 squared means that all of those numbers cancel out, And what we're left with here is that the diffusion coefficient via the vacancy mechanism is the individual atomic jump frequency times the lattice parameter squared. So that actually works out really conveniently. But now we need to relate the vacancy diffusivity to the self-diffusivity via the concentration of the vacancies, because every vacancy is the opportunity for diffusion to occur via that vacancy. If the concentration of vacancies is 0, then obviously the diffusion coefficient for the vacancy mechanism would be 0. And every time you create a vacancy, that gives you another opportunity for diffusion along that mechanism. So we get the concentration of vacancies here, x sub v, via e to the minus the Gibbs free energy of formation of those vacancies, g sub v, over kT. So the higher the temperature, the more vacancies that you would expect in your crystal. This Gibbs free energy of vacancy formation can be divided into entropic contribution here, S sub v, and the enthalpic contribution, H sub v. And then the self-diffusivity then is related by, so D, this would be the self-diffusivity of the atoms, is equal to something called a correlation factor F times the diffusion coefficient of the vacancy times the concentration of those vacancies. So it's the correlation factor here, F, times gamma prime V, times the unit cell parameter A squared, times then our concentration of vacancies given by e to the minus gv over kt. This correlation factor is what accounts for the effect that I mentioned earlier, where suppose an atom hops off of the corner site here into the vacancy position. What is the next most likely thing for that atom to do would be to jump back into the vacancy that it just left behind. And so the net effect there of just hopping back and forth is 0 when it comes to the overall diffusion. And the correlation factors accounting for these geometric factors that tell us how much of this jumping actually contributes to overall diffusion. So this correlation factor F is included because the jumping sequence of an atom is not random. If an atom jumps into a vacancy, its next jump could be jumping back into the vacancy from which it had just exchanged. That's the most likely thing for it to happen. Or it could jump into another vacancy that is in another nearest neighbor site. Or it could wait for a while for a new vacancy to arrive in another nearest neighbor site and then jump into that one. So the correlation factor here, F, is a ratio that connects the actual diffusion coefficient relative to that if the diffusion were purely random. And this involves an average of considering the angles, the cosine of the angle between subsequent hops. These are the off-diagonal terms that came in when doing the mean squared displacement calculation. If this average here is completely random, so if the angles here are completely random, then this average becomes 0 and the correlation factor is 1. So for a purely random walk, the correlation factor is 1 because this double summation here is 0 because the angles are random. On the other hand, if there is exact anti-correlation between subsequent jumps, if the atom is only jumping back and forth all the time, then the second term here becomes -1, and the overall correlation factor is F equals 0, which means that there's 0 contribution from that event to the diffusion coefficient. Now, if we account for all the jump trajectories in an FCC crystal, and consider the vacancy mechanism with that FCC geometry, the correlation factor is found to be F equals 0.78. And there is a table of these in the textbook. I got these values from another textbook from Manning, Diffusion Kinetics for Atoms in Crystals. And you can see for these various 2-dimensional lattices, 3-dimensional crystal structures, then this upper part of the table is vacancy mechanisms. The lower part is interstitialcy mechanisms. All of these correlation factors here are compiled for each of these cases. So it's often the case that one would just be able to look up the correlation factor that corresponds to that particular mechanism for that particular crystal structure if it has already been determined. So that was diffusion in metallic crystals. Next up is diffusion in ionic crystals. And this is more complicated because the diffusion is necessarily charged species, ions, and we have to maintain local electrical neutrality. So anytime there is a defect in ionic crystal, there is a charge associated with that defect, and there must be at least one other defect with the opposite charge in order to maintain local charge neutrality. So the notation that we use to describe defects in ionic crystals is Kroger-Vink notation. This is the standard notation for describing defects in ionic crystals. And this notation is relative to that of the perfect crystal. So let me go through some examples. First, let's consider interstitial aluminum. The big font here is the species that is at the defect site. So this is, in this case, an aluminum ion that is occupying an interstitial site. So the aluminum ion is the species, so that is the big font. The subscript is the site where it's located. So this little I here is an interstitial site. This is an aluminum ion occupying an interstitial site. And then the superscript is the charge of the defect relative to that of the perfect crystal. In the perfect crystal, there's nothing in the interstitial site. The aluminum ion has a +3 charge, which means that the aluminum interstitial has a net charge of +3 compared to that of the perfect crystal. And we denote that +3 charge by 3 dots here. So each dot represents a positive charge. 3 dots means a +3 charge. So this is the Kroger-Vink notation for an interstitial aluminum. If we move over to the left, this shows a magnesium vacancy. In this case, the V here means vacancy. If you're dealing with a vanadate system, make sure you use maybe a capital letter V for vanadium, a lowercase letter v for the vacancy, or use a script letter or something to distinguish the two. But in this case, since we're dealing with a magnesium system, we can just use the letter V for vacancy. So in this case, we describe the defect by having the species that is at the defect site, that is the vacancy here, V. The location of the defect is magnesium. So this is a magnesium latticed site where we have a vacancy. Now, magnesium has a +2 charge, which means if you take away the magnesium ion and replace it with a vacancy, which has a 0 charge, the relative charge of the site compared to the perfect crystal is -2. It is 0 minus a +2, which gives you a -2 relative charge of that magnesium vacancy. And we represent these negative charges with primes as the superscript here. So 2 primes means a -2 charge of the magnesium vacancy. Another type of defect would be a substitutional defect. For example, if you have an iron 2+ ion substituting for a magnesium 2+ ion, the species on the defect site is iron. It is occupying a magnesium site here in the subscript, and the net charge relative to the perfect crystal is the same, right? It's a 2+ ion going in for another 2+ ion, so 2 minus 2 is 0. And so we denote that if we have a neutrally charged defect with the letter X here. So the dots indicate positive charges, the primes indicate negative charges, and the X indicates a 0 charge. Another example would be, what if you had an iron 3+ substituting for a magnesium 2+? In this case, the iron is the species that's on the defect site. The site is the magnesium site. But now the iron has an excess of 1 positive charge compared to the magnesium. 3 minus 2 is a +1. So we've got 1 dot here to denote that. Now, point defects in ionic crystals occur at least in pairs. They occur in combinations. And 2 of these basic defects are the Frenkel defect and the Schottky defect. The Frenkel defect involves taking an ion from its lattice site and putting it into an interstitial site. So the pair of defects here is the interstitial defect and then the vacancy that it leaves behind. And if you combine the interstitial site and the vacancy site, this has a net neutral charge. The Schottky defect involves taking away both the anion and the cation. So if you have both anion and cation vacancies, then if you've got the right combination of those vacancies, that would have a net neutral charge. So a Schottky defect is a combination of cation and anion vacancies. A Frenkel defect is creating an interstitial by leaving behind a vacancy of the same type. So we can use this Kroger-Vink notation to write defect reactions for the creation of these defects in ionic crystals. For example, if we were to create a Schottky defect in magnesium oxide, we start off with the perfect crystal without any defects, and that can be denoted either by writing out null, using the null symbol, which is the 0 with the slash through it. This is the perfect crystal on the left-hand side, and from the perfect crystal, we are creating a pair of defects, which would be a vacancy of the magnesium. Since magnesium has a +2 charge, the vacancy has an effective -2 charge, hence the 2 primes here, and then a vacancy on the oxygen, which has an effective +2 charge. So the combination of these two defects is charge neutral. 2 negative charges, 2 positive charges cancel each other out. If we have the Schottky reaction for a more complicated species, such as barium titanate, here the full Schottky reaction would be creating 1 barium vacancy, which has a -2 charge, 1 titanium vacancy, which has a -4 charge, and then according to this formula, 3 oxygen vacancies, each having +2 charge. So this is a total of 6 positive charges and a total of 6 negative charges. So they cancel each other out, and you have net charge neutrality. Now, with something like barium titanate, you don't necessarily need to have the full chemical formula leaving behind vacancies. You could, for example, get charge neutrality with a partial Schottky defect. For example, 1 barium vacancy and 1 oxygen vacancy would be charge neutral, or 1 titanium vacancy and 2 oxygen vacancies would be charge neutral. If it doesn't involve the entire formula, that's what's called a partial Schottky reaction. And to give an example of a cation Frenkel reaction here, creating cation Frenkel defects, if this is in silver chloride, the cation here is the silver ion, which has a +1 charge, and the Frenkel defect involves taking one of those silver ions, putting it onto an interstitial site. So this is silver on an interstitial site, which has a charge of +1, and then leaving behind a vacancy on the silver site, which has a charge of -1. So if we consider now, what about a Schottky pair, a Schottky defect pair in potassium chloride? Going from the perfect crystal here, null, so no defects, to creating a vacancy of potassium, which has a -1 charge, and a chloride vacancy, which has a +1 charge. What determines the concentration of these vacancies? This is determined by the equilibrium constant, which is determined by the free energy of formation of that defect reaction. So this G sub S with a superscript F, this is the Gibbs free energy of formation of the Schottky defect. It is the Gibbs free energy that is associated with this defect reaction. This is equal to -kT times the natural log of the equilibrium constant. This equilibrium constant, therefore, if we solve for that, it's e to the minus Gibbs free energy of formation of the defect over kT. And this can be written as the product of the activities of everything that is on the right-hand side of the equation here. And if we assume Raoult's law for dilute solutions, then the activities can be approximated by the concentrations. This is true because the defect concentrations are generally small. And so what we get is the product of the concentration of the potassium vacancies with the concentration of the chloride vacancies equal to the equilibrium constant. So it's the product of the concentrations of everything on the right-hand side of this equation equal to the equilibrium constant, which is equal to e to the minus Gibbs free energy of that reaction over kT. The next thing we need to do is solve for the concentration of one of these defect species. So we also need to take into account the stoichiometry of this reaction, which for this system is very straightforward because for every potassium vacancy, we have the same number of chloride vacancies. So we know that the concentration of potassium vacancies equals the concentration of chloride vacancies. So setting these two equal to each other, that is equal to then the square root of the equilibrium constant, which is the square root of this exponential, which means that we have a 2 that comes into the denominator. So this is what gives us the concentration of those vacancies. If you have something a bit more complicated, like calcium fluoride, here, because of the stoichiometry of this crystal, for every 1 calcium vacancy, you have 2 fluoride vacancies. So then the product of the right-hand side of this equation is the concentration of calcium vacancies times the concentration of fluoride vacancies squared, since that appears twice. This is equal to the equilibrium constant, which is equal to e to the minus Gibbs free energy over kT. Now, the balance is slightly more complicated because of this charge difference, the concentration of calcium vacancies is 1/2 of the concentration of fluoride vacancies. So for every 1 calcium vacancy, you'd have 2 fluoride vacancies in order to account for that. So if we take this substitution into this equation here, we can take this concentration of the calcium vacancies, that's equal to 1/2 the concentration of the fluoride vacancies. So this left-hand side of the equation becomes 1/2 concentration of fluoride vacancies cubed, and that is set equal to the equilibrium constant. So solving for the concentration of the fluoride vacancies, we multiply both sides of the equation by 2, and then take the cubed root of both sides of the equation. That gives us the concentration of fluoride vacancies, which is the cubed root of 2 times the equilibrium constant. That's equal to the cubed root of 2 times e to the minus Gibbs free energy over 3 kT to represent that cubed root. That gives us the concentration of fluoride, and then the concentration of the calcium vacancies is just 1/2 of that. Here's another example. This is for a Frenkel defect. This would be a cation Frenkel defect in silver bromide. The reaction in that case goes from the perfect crystal on the left, so no defects, to creating a silver interstitial, which has a net +1 charge, and then a corresponding silver vacancy, which has a -1 charge. Here, taking the product of the concentrations on the right-hand side of the equation, we've got the concentration of the silver interstitials times the concentration of the silver vacancies equal to the equilibrium constant, which is equal to e to the minus Gibbs free energy of formation of the Frenkel defect now over kT. Knowing that for every interstitial there is a vacancy, we know that these two concentrations are equal to each other, so they're equal to the square root of the equilibrium constant, which is equal to e to the minus Gibbs free energy over 2 kT. So let's put this to work in a real example to show you how we can use this to get both intrinsic and extrinsic mechanisms for diffusion in a sodium chloride crystal. So let us consider diffusion of sodium ions in a sodium chloride crystal as governed by the vacancy mechanism. And let's consider 2 possible sources for sodium vacancies. First would be an intrinsic mechanism, which is due to Schottky defects. The Schottky reaction here would be starting from the perfect crystal. Let's produce a sodium vacancy and a chloride vacancy. And then the second source of sodium vacancies would be due to a substitutional defect reaction by doping the sodium chloride with some other substance. In this case, we're going to pick a divalent chloride salt, cadmium chloride. So the cadmium has a +2 charge, so that's twice as much as the sodium's charge. In this case, we're doping cadmium chloride into a sodium chloride matrix. The chloride ion goes on the chloride site. There's 2 of them. That has a net neutral charge. But now the cadmium, which has a +2 charge, is going to go onto the cation site in sodium chloride, but the sodium is only +1 charge. So we've got a +2 cadmium going onto a +1 sodium site. So the net charge of this substitutional defect is +1, which means that we need to have a corresponding defect that has a negative charge. And since each cadmium is replacing 2 sodium sites, in addition to the substitutional defect, we also need to have a sodium vacancy. And the sodium vacancy has an effective -1 charge. So now we've achieved local charge neutrality. And now you can see that you've got 2 different sources of sodium vacancies. This first one is the intrinsic mechanism, which comes from Schottky defects. And the second one is the extrinsic mechanism, which comes from doping. So if we consider first this Schottky mechanism, here's our defect reaction. The concentration of sodium vacancies from the Schottky mechanism, using the subscript S, this is equal to the square root of the equilibrium constant for that reaction. So this is equal to e to the minus Gibbs free energy of formation of that Schottky defect over 2 kT because of the square root there. Now, what is the concentration of sodium vacancies from the extrinsic mechanism from this doping reaction? This is more straightforward. You can see from the stoichiometry of this reaction that for every cadmium ion that you put in, you get the same number of sodium vacancies. So the concentration of sodium vacancies from the extrinsic mechanism is simply equal to the concentration of the dopant, the concentration of cadmium chloride. Therefore, the total concentration of sodium vacancies here is equal to the summation of all the sodium vacancies you get from the Schottky mechanism, plus all the sodium vacancies that you get from the extrinsic doping mechanism. So that would be equal to, from the Schottky mechanism, e to the minus g over 2 kT, plus from the extrinsic mechanism, simply the concentration of the dopant, cadmium chloride. So let's put this together now to get the diffusion coefficient of sodium via the vacancy mechanism. So from here, we have, let's consider that we've got the diffusion coefficient of sodium. This would be equal to the population of your sodium vacancies, so the concentration of sodium vacancies, including both mechanisms, intrinsic and extrinsic mechanisms, times the correlation factor for that crystal, times the jumping distance squared, times the vibrational frequency, times then a migration free energy factor, which is e to the minus delta G star. This is the free energy associated with the migration of sodium to actually make the jump over kT. So let's consider first the extrinsic regime of diffusion. Here you can see this is the natural log of the diffusion coefficient versus 1 over temperature. You've got 2 regimes that will result here that are 2 Arrhenius scalings here. So the straight line regime here at high temperatures is the intrinsic regime. At high temperatures, this is where the intrinsic mechanism dominates because the Schottky defect reaction produces more defects. At low temperatures in the extrinsic regime, it is the dopant that is dominating here. So let's consider this extrinsic regime first. In the extrinsic regime, the concentration of sodium vacancies is simply equal to the concentration of the dopant. And therefore, the sodium diffusivity in this regime is just the concentration of that dopant times this prefactor here, times our e to the minus Gibbs free energy of migration of the sodium over kT. And this Gibbs free energy of migration has an entropic part, which can be brought out in front, and then the enthalpic part. So when one takes the natural log of both sides of this equation, you've got a lot of factors out here in front, which are just the constant. And then the slope is simply minus the delta H star over K. And that is our slope here on the Arrhenius plot. So the slope of this plot times minus Boltzmann's constant gives you the activation enthalpy for the migration of sodium for this extrinsic mechanism. What about the intrinsic mechanism? Note that this has a steeper slope, and let's find out why it has a steeper slope. So here in the intrinsic regime, the concentration of sodium vacancies is given by the Schottky reaction, and that is then given by, here, e to the minus Gibbs free energy of the Schottky reaction over 2kT. Both the Gibbs free energy of the Schottky reaction and the Gibbs free energy associated with sodium migration have entropic contributions, which get pulled out into the front. They become part of the prefactor. And then enthalpic contributions shown here. You can see that there are two contributions then to the slope of the Arrhenius plot. There is the same contribution that we had from the extrinsic case, which is the minus delta H star over K. And then there's an additional contribution to the slope, which is this minus HS over 2K. So our slope here in the intrinsic regime is steeper because there are two contributions. There's the amount from the Schottky defect reaction here, and then the amount from the sodium migration. And that's why we end up with a steeper slope in the intrinsic regime. So this, when we put this together, this shows the overall diffusion coefficient of sodium accounting for both mechanisms. Accounting for both mechanisms, we include both terms here from the extrinsic and the intrinsic regimes. And the crossover occurs where the number of intrinsic vacancies equals the number of vacancies due to the extrinsic dopant. At all temperatures less than that, the extrinsic regime is dominant, and we're dominated by the dopant. And all temperatures greater than that, then we are in the intrinsic regime. So to summarize, atomic mechanisms for diffusion in crystals include ring, vacancy, interstitial, and interstitialcy mechanisms. Vacancy diffusion in crystals includes this geometry-dependent correlation factor. When we go to ionic crystals, we can use Kroger-Vink notation to represent point defects and write the defect reactions. And diffusion in ionic crystals involves multiple species and can include both intrinsic and extrinsic regimes. Now, everything here was just a single crystal. Next time, we're going to consider diffusion in polycrystalline materials. So thank you very much for listening.